We'll try to divide the webinar into 4 sections. So first 15 minutes we will focus on the valve body selection. Then the next 15 minutes we'll focus on the trim selection, especially which type of trim to be selected, and we'll try to have some kind of thumb rules or kind of like an algorithm, so that when you make your data sheet you have a basic idea of, okay fine, for this application this should usually be the trim type selection. Then next we will look at material selection. Again, these 4 points I have come across by your questions only over the years, at least for the past 8 years. Whenever I have seen, these were usually the 4 questions, and the final one was control valve standards also, at least. And you should have an overview, not in depth, but at least you should know the basic international standards that are applicable when it comes to control valves. First is the selection process. So let us first start with understanding the valve body selection as a first case. So I would start here by explaining is basically, if you want to protect yourself, and should you use a mosquito repellent or should you use a machine gun, for example. Now this question sounds ridiculous, but if you actually look, the answer is not clear. It depends on what is in front of you. If it's just a cockroach, the mosquito repellent or the cockroach repellent would be very good for you. But a machine gun, even though is better, but it's over specified. So the first thing in the valve selection, which some of you said in the comments, is basically to understand the exact application. Once you know the application, we will go into details of what in the application you should know, but the point is, first you should know the application. Where do you want to apply the valve? And that is where we go forward. For example, if you have a dinosaur, for example, your mosquito repellent would definitely not be sufficient for that case. In that case, you definitely need a machine gun, even though it is costly. So you should know the cost difference between various kind of valves, but that is not the only criteria to select. First is you need to know what you're dealing with, and then you can select based on your application. For example, how can you be cost effective plus technically compatible at the same time? Let us look as to how to understand a particular application. Now when we go here, the first thing we need to understand is the application requiring precise flow control or not? Let me give you an example. For example, let's say you have a utility service. Now utility service, you don't require it to be completely precise. However, if you are exporting or if you are having petroleum products, or for example it's a paint line where you need to mix in a certain proportion, there your precise flow becomes very important. In that case, you have to first know is how is your application, does it require very precise flow or not? Second thing is differential pressure. Okay, one of my friends in Shell, he told me one thing to remember. If you want to do control valves, differential pressure or the pressure drop across the valve is going to be your number one characteristic that will help you to understand which valve, which trim, in control valve sizing, in selecting the correct CV. For everything, your DP becomes extremely important. So this is what we have to pay very attention. How much is the differential pressure? It is less, for example 5 bar, 2 bar, or if it is 50 bar, 100 bar of pressure. So as the pressure changes, your selection has to definitely reflect that. Third thing is what I call as CFC and issues. We will deal with that as we come there. And finally is your budget. Least in the list, but according to clients and your end users, definitely that is one of the most important thing to them. But as an engineer, I put that at the last. First is because to understand that if it follows the first 3 criteria, only then can you look for budget. If your valve cannot cater to application, it doesn't make sense even if your valve is the most cheapest. Then you have some smaller parameters also, like the leakage requirement, line size, and other, I think around 20 parameters, but these 4 have usually been the strong parameters while deciding any application. Now first let us look into the cost effective pattern. Okay, now when you get to cost effective pattern, what I would suggest is there are a lot of valves available with us, but with respect to their design, not all of them are good for control. So let us ignore as of right now is gate valves and the common ball valves. We'll keep segmented ball valves, plug valves with us, plus we'll keep is globe valves and butterfly valves, because these are usually the 4 types which are usually used for control applications. For special applications you have diaphragm seals, diaphragm type valves, etc. But those are very, very high viscous applications and very specific industry related stuff. So let us first discuss this overall as a graph. Now when it comes to your application, you have butterfly, segmented ball and globe. Now here, which is the most cost effective option? Ideally speaking, in a very broader picture, butterfly valves are usually the most cheapest. Then comes your segmented ball and plug valves, and then comes your globe valves. If you see logically also, a butterfly valve is a very thin valve with completely, the material itself used to make it is less. Then comes your segmented ball or plug valves, and then if you see the globe valve design with respect to its complex flow path, it is very difficult to manufacture it very cheaply. So comparatively, if you see, butterfly we can keep as of now as segmented ball and plug, and then the globe valve. I would say maybe you can imagine the butterfly valve, just for our understanding, kind of like the cockroach. So wherever the application is simple, as an engineer, your first chance is to see whether can you have butterfly valve implemented there. If that doesn't work out, then you look for whether segmented plug can work or globe can work. Now let's look into the second important point, size. Okay, now the budget will greatly depend on your line size. So as somebody said in the comments very clearly, as the line sizes increases, the impact of the size on globe valve will become 2 times, 4 times. It will increase dramatically as your line sizes increases, and also the maintenance will become tougher. So in that case, if your line size is very large, first look, can you make butterfly valve fit in your application? If not, then look for segmented ball or plug valve design, and if nothing works out, then maybe you can look for a globe valve design, or you should consult a specialist if the line size is too big, because globe valve maintaining at such high line sizes and with such a huge pressure drop is something tricky. The second application or the point which we discussed was precise flow. Now when it comes to precise flow, we have globe, segmented ball, plug, butterfly. Can you tell me which one has the most precise flow control capability available with them? Globe has definitely the winner. You go to any control valve, whether you go to manufacturer, you read any reference book, any standard, globe valve definitely wins here. They have very precise control. So if you are having some petroleum products, etc., definitely you should first go for globe valve regardless of the cost, if you want precise flow control especially. Critical application here is CFCN. What I call CFCN is cavitation, flashing, choked flow and noise. For these 4 issues, which is usually what a control valve mostly faces, here the valve selection again becomes important. If you have any of these 4 criterias, then which valve is better for you? In terms of the solutions for such cases, if you see, the CFCN is basically also having a relation to differential pressure. What I mean by that is, if you would look into your control valve sizing, or if you have already done, you would notice that the applications which have higher DP, which have challenging DP values, would mostly be experiencing these CFCN issues, which is cavitation, flow, flashing, choked flow, noise, etc. So I would see kind of they are interrelated to each other. So for applications which have high differential pressure, or you have already experienced CFCN happening through your calculation, for those applications, which valves should you choose? The answer has to be, out of the 3, it is definitely going to be globe valves. Why is that the case? Is because globe valves, first of all, they have a lot of options. For example, if you want low noise trim, you want to have different kind of characteristics, it becomes easier when it comes to and handling. If you see a butterfly valve, in terms of its construction, it's basically a vane which is rotating. So now imagine at especially I would say 60 or 70, 80 degrees, that is when at that time to maintain its state at a very high DP, let's imagine 100 bar of DP, it's too difficult, it will start to vibrate here. So it's very difficult. You have certain valves which have come in the market, which are called as triple offset butterfly valves, but still it is very tricky to maintain that kind of position in such high differential pressures. So for that case, I would definitely suggest is that you should definitely go for globe valves as long as it is possible, and then you can have in the middle, which is your segmented ball or plug valves to be used in case if you can cater to those applications. Now getting to industries, can you tell me generally for oil and gas, which is the most common type of valve used? For pulp and paper and for wastewater? Based on what we learned, if you also apply it to industries, you will generally see that for oil and gas, which majority of you have answered and seen in your books, is that the traditional sector preference is globe. Now when I say globe for oil and gas, does not mean that it should be globe for any XYZ project, XYZ line. It should definitely depend. In oil and gas also you have utility section where you will have water transporting. So there if you see a globe valve, you can definitely try to replace that with a butterfly valve and save cost and maybe have a value addition as an engineer in the project. So but overall speaking, because oil and gas projects are generally more challenging in terms of their differential pressures that you will face, for example a ethane cracker, so all those projects generally you would see that all engineers usually recommend a globe valve. When it comes to pulp and paper, it is not extremely challenging but not that easy as just water treatment plants. So generally they have a generally they have a preference for segmented ball or plug valve design. And finally, when it gets to wastewater, most of you answered because those are not challenging applications, you might first try to go for a butterfly valve. So we'll make a quick summary. So first, as an engineer, when you're looking, you will see, do you have these three issues there: CFC and high differential pressure or precise flow control? If that is the case, the answer is yes, then you should look for globe valve, which is your most costliest option, but you have no choice as an engineer. If no, then you can look for some budget friendly options. For example, you will first try for butterfly valve. If butterfly doesn't work, then maybe you can look for some more tough applications, for example segmented ball plug valve, which can be in the middle. So basically you have is the best is the globe in terms of the overall applications, but the most costliest one. In the center you have is ball or segmented plug valve, and finally you have is the butterfly valve, which is the most cost effective option. Trim type selection. Now this is definitely very confusing when it gets to especially globe valves. So when you get to trim for globe valve, you have plug guided trim, you have balanced type, unbalanced type, cage guided, trim guided, single port, double port. Then you have characteristics like linear, quick opening, equal percentage. So now with all of these different types, it becomes very confusing how to mix and match them together based on a particular application. For trim type selection, first I would like to make it at least divided into subcategories, and then we will explore them. So the first category which I call is unbalanced and a balanced trim design. Then the second opposite side on the spectrum is basically where you have linear characteristics, quick opening and equal percentage. Then you have something called as cage guided design and plug guided trim. And then finally you have is dual port and single port globe valves available. First thing is, I want to explain this concept of how these trims come into picture with something related to civil engineering. Now in civil engineering you have something called as cantilever. Now cantilever is basically a very simple design. If you see, cantilever means a support which is given by civil department, which is fixed at one end and the other end is unsupported. So basically, if you want to remember, I don't know, if you have instrumentation trays which have to be laid, civil gives you this kind of support. So one side it is usually fixed and the other side is usually, because the trays are not very heavy, so they can easily rely on the beam that is given. Now that being the case, how does this basically help in our trim design? Let us look into that point. This design is kind of similar if you see to a valve connected to a plug. If you see here, the top side is basically the fixed end that we have, and the bottom is something which is free, which is the unsupported end that we have. If you see for any valve application, for example here, this is how your fluid is flowing through the valve. Now when you look here at this design, you can see that because it is supported at one end, the other end, if there is huge amount of I would say turbulence, or for example very high dp, it is very difficult to keep the other end stable. It will start to kind of oscillate, and this is especially not good for a valve which needs to have precise flow control. And that is how came your dual ported design. Now what happens here is, in the dual ported design, if you see here as the way it is moving, it is supported at the fixed end, which is from the actuator side, and at the bottom also it is supported. So how this was helping was, if you have very high dp, this is just I'm giving you a example, maybe 30 bar, 50 bar, it depends on your application. We will look in the end as to when do you select dual ported design, but just giving an example, if the DP is high, then your plug is definitely going to oscillate a bit. So it is better from single port to go to a dual ported design. You would see in majority of the chat, very few people said dual ported design. If this design can cater for high DP, and most of you have your experiences in challenging applications, why didn't you select a dual ported design compared to a single port design? So basically with dual ported design, as some of you said, there is going to be an issue. So but overall, remember one thing, when it comes to dual port and single port valve plug guided is good for low differential pressure applications. Dual port is good for high differential pressure applications. Okay, then now let's look into answering the question why it is not used in most of the applications. The first important thing is leakage paths are increased. You have one point of contact with the fluid. There, if the shutoff is not good, you will have some fluid leaking. If you have two ports, definitely it's going to have 4 paths of leakage available. Second is higher cost, because the body size is going to definitely increase. Then you have the third thing is they are heavier. Because of the two ported design, they make it far heavier valves compared to your regular application. Then this bigger design also has to be accommodated. Again, that becomes difficult for the size to be available in the plant, the clearance is available to remove the valve out, etc. So all of these factors were actually having an issue, and up till 1960s engineers had no solution. So it was very clear for them at that point of time, if it's less DP, low DP applications, I go for a single port valve. If it's heavier or high DP applications, I will go for a dual ported design. That was it. But then what happened here is, what I would like to share is the idea of cage guided came into picture. Now what happens with cage guided is, we will get to the characteristics of trim, but before that what I wanted to explain was that cage guided, why did the need come for cage guided? If you see here, a lot of people also said in high DP I use cage guided valves. You are correct. What happens here is, in cage guided design is the top end is anyways fixed, basically with some kind of support. The bottom here is also fixed because the cage will never move. It is the plug that moves inside the cage. So now you have better stability at high differential pressure applications, and this reduces the idea of leakage path. This reduces the idea of having a bigger design or two ports available. Also the space requirements have reduced. So this seems to make a lot of sense. However, there is a big however. If your service has big solid particles which could get plugged into your cage, then maybe you need to still think about dual ported design. They are not traditionally used. Most applications you should avoid them. If nothing works out, and if you know your fluid is that much tricky, then maybe you might need to go for a dual ported design. Otherwise, if it's high DP, you should go for a cage guided design is a better choice. The balanced and the unbalanced trim design, and then we will club all of these trims together and try to make a kind of like an algorithm. So now here, when I'm trying to talk about balanced or unbalanced design, if you see here, this is the plug, this is the seat assembly available, and this is the fluid forces which are hitting to it. Now what is going to happen is, the fluid forces, let us call it as P2, and the actuator force is P1. If I want the valve to be closed, P1 has to be greater than P2, which makes sense, right? If actuator force is greater, it is going to close and not allow the fluid to enter. This means the actuator has to put all the power. When you go for a balanced trim design, if you see there is this small hole here, what does this small hole do over here is, at this particular portion, is that once you have that hole available, the fluid forces can enter through the hole and go to the opposite side. Once they go to the opposite side, the actuator and the fluid forces become friends with each other, and it's kind of like they'll further support and allow the force to add up. So for example, the fluid force was P2, and on the other side you have actuator force P1 plus P2 acting from the opposite direction. So this greatly reduces your load on the actuator. When is this design good? It is good when you have very high DP or your line size is too large, because if your line size is too large, your actuator sizing will become again big. So either if your DP is too high, so even if the line size is small but the DP is extremely high, you should still go for a balanced trim design. Why? Because it will save a lot of your cost in terms of the actuator sizing. But again, there is a big but. The reason is, if your fluid even has smaller solid particles, still they'll get stuck in your balancing hole and your actuator will not be able to function well because it is not designed for that high pressure. Now, why am I telling you this? Is a lot of times what happens as engineers is, you give a requisition for a particular vendor. The vendor will definitely has to save cost. He would not see any clause maintained in your data sheet saying that there is going to be some solid particles. You missed to mention that clause, and he gives you a balanced design. Now when it gets to plant, your valve will actually, that hole will get stuck and your valve will not function properly. It will not close and you will have extremely high leakage rate. First thing. Second thing is, if you can see my mouse here, once the fluid enters here at this particular point, again there's going to be another leakage path available. So your leakage chances also increases. So again you need to be very cautious that are you okay to have slight amount of leakage available here. Now let us look into the trim selection chart. So first you have to see, which I told you initially, a friend of mine has always been an advocate of DP. So if the DP is high or not, DP is like 1-2 bar is like very minimum. As the DP increases 50 bar, 100 bar, you have to understand how is the DP. Once you know that, then you look for, is the line size large? If the line size is also not large, then you should go for a single port plug guided. Plug guided means the plug itself is contoured to that level instead of cage guided. You might go with plug guided, should be okay for very small size. The DP is also less. Go for that, save your cost. If that is not possible, if your DP is very high, then you see whether the service is clean or not. Because if your service is dirty service, even if you have something like unbalanced trim or cage guided, then you have to look how dirty is the service. If your service is clean, the answer is yes, and your line size is also large, then you should prefer to go with a balanced trim design with a cage guided design. So inside the cage guided with a balanced trim is your best choice to go. If your service is extremely dirty, it has very hard and strong particles which are there, in that case maybe you might have to go for a dual ported valve so that the valve stays in its position at very high DPs, and it has a lot of dirty fluids, it still should be able to handle it. But this side can be discussed with your valve vendor and you people can come together and find if there is some other solution. If not, then maybe you might have to go for a dual ported design. Now in this algorithm, what we have yet not considered is the characteristics, whether it's going to be linear, equal percentage or quick opening. So now let's look at only that part. I would maybe give you a golf example to make that point. Is example, if you see here, I need to reach to point A1, which is the winning point, okay, and you have B1 and C1, two different points for hitting the golf ball. Whenever I hit a ball to reach to A1, there is wind which acts and causes my ball to fall in B1. So now what is an engineer's mind here? You can't control the wind, but you can definitely control your stroke and your ability. So what do? Is you aim for C1. So you know that as soon as I aim for C1, eventually the wind is going to come, which is a uncertain factor, but to kind of extent you can manipulate. Okay, fine, okay, it causes your valve or your basically ball to move 10 centimeters behind, and then you get to A1. So basically you try to understand how the non-linearities of wind works, and then eventually you get to your point. This is the same concept when it comes to your valve characteristics. There's a lot of different literature available when it comes to your characteristic selections. A lot of people have their different opinions. I respect all of them. This is what I personally find it to be valuable and what I usually use. I'm sharing it with you, and I will also explain the concept. Then it is on to you to decide of how you want to select your characteristics. They mention something called as del P max by del P min, which is under the ratio of 2:1 or higher. So the overall concept is very simple. The concept is that if you have variations in the dB, ideally you are expecting your valve to be linear. Everybody wants the valve to be linear. But because you can't control the DPs in the plant because they are continuously fluctuating, if the DP variation is high, which you see on the right hand side here, the percentage selection should be usually be equal percentage there. If your DP variation is less in and of itself, you should usually go for linear. However, there are certain people who recommend certain type of characteristics based on application. We will also look into that point. So for trim characteristic selection, I would say, is the DP fluctuating? Is it greater than 2:1? Is it fluctuating? No. Then go for linear characteristics is usually recommended. Then if your DP fluctuation is higher, you should go for equal characteristics. Most of you people who are working, you might have selected equal percentage characteristics. Sometimes it is just because you found in some other data sheet and you copy and pasted the same data, which is not correct. But most applications are tricky for us. But when it gets to applications, we can also have this thumb rule that usually level applications are kind of simple. So usually you might see linear mentioned more there most of the times. When it comes to flow or pressure applications, these are kind of fluctuating a lot. So usually you will have equal characteristics trim mentioned here. But I would say go with this rule of 2:1 and 5:1. Less DP fluctuation, go with linear. High DP fluctuation, go with equal percentage. Third important thing is material selection. I have got a lot of questions from engineers asking about material selection. First, before we select is to know how the materials are actually named in their way. So for example, when you see UNS numbering system, you see something like this mentioned here, where this is your main material and this is your subgrade. Now this subgrade will vary. For example, 316L, you have 03 written in the end. So some vendors give you materials mentioned in this format. Sometimes you might have something in the ASTM format. Here you would have is like this grade, which is the let's not answer first. You have these two grades available here, which is actually nothing but 316. One is the forged grade and one is the cast grade. The forged grade is something which you beat up and then you make it. Cast is where you cast it into a mold, it gets cold, and then that's how you get the material. Now why has ASTM done this is because you have more grades also with ASTM, but the reason is that forged grades are generally considered to be very hard compared to the cast version. As an engineer, why I stressed this point is, I would not name, but after talking to few vendors, there are certain companies for a certain valve material, they want it to be forged. So if the vendor has given the cast version of that valve, the valve body, it was rejected and at a very later stage. So the vendors be very cautious. If the vendor gives you UNS numbering system of the material, you don't know whether it is a cast grade or it's going to be a forged grade. And there are certain, I'm talking about world renowned companies that could reject by saying that no, they want the forged grade and that is what is specified in their specification. So be very cautious of this point as well, and that is the reason why I put this here. So both of these stand for nothing but 316. That being said, the DIN is another numbering system which is kind of like more confusing. 1.4401 has nothing to do with like 316 mentioned anywhere near to it, but it is the 316 grade, and in the end if it ends with 04, it's 316L. So again, in this you don't know whether it is forged or cast. So first thing is you should know if your application is requiring which kind of material. And I would like to give you some thumb rule. If your line size is small, vendors can give you forged version. If your line sizes are too huge, it is difficult for them to give you forged version. If it is still mentioned in your spec that they want a forged version, then you should definitely raise this, I would say, leniency here when it comes to very large sizes. Now in terms of materials, as you said, it depends on particular service. I would also like to add, like a chef who puts spices to make a particular food, you need to know at least the basic components and how do they fit in when it comes to your application. So you have chilies, you have pepper, you have something. If you want to make something spicy, you will add more chilies into it. If you want to make something sweet, you would add sugar into it. When you mix something in a food, how its taste changes, similarly when you mix something in a material, its composition is going to change. Now getting to your question, that if the pipe material is mentioned something like 13% chromium Cr, can I select SS316? I would want to answer this after we get maybe to the end of this part. So the first thing here is, I would compare chilies to be like carbon. You know, the more you provide, the more hotter the food gets. Similarly, carbon makes the material harder. The more you provide carbon, the more the material becomes harder. That means if I want to have an so that is why you would see a lot of pipes of piping are made of carbon steel, especially. Okay. One thing is, as these things become harder, they'll also become brittle at the same time. Example is glass. Glass is hard, but if I break it, it's very easy. It's brittle. So I can't keep adding carbon all the time. Similar to chilies, I can't keep adding chilies to make the food spicy. At a point of time, it becomes unbearable. Second thing is, why is this carbon thing important for you to know is, if you imagine carbon steel line and if you have SS316 valve body, so you might be more corrosion resistant than that. But if you go to your flange ratings, they will be inferior because they are not as hard, because carbon steel is harder. So maybe you might have to up your ratings. So that is how you should have an in-depth understanding that, okay, I don't have carbon in my valve, so my body rating and the flange rating will be higher to match that of carbon. But corrosion resistant wise, I am better than carbon. SS316 is better. Why it is better also we will get into that. But so remember, carbon is what personally I remember it as the chili. Use it as much as you want, but at a point of time, if it becomes too much carbon, it's going to make a very your material to be very hard. The second one which comes in as sprinklers is going to be chromium. Very important. The higher the chromium, the higher the ability to prevent corrosion. So when you have any carbon steel pipe and a stainless steel pipe, almost every one of you will answer that carbon steel pipe compared to SS316, the 316 will have higher corrosion resistance. Very simple. The reason is because we have put chromium into it. Now let's answer that question. So if the piping has 13% chromium is the pipe material, as an engineer, if you select SS316, the chromium percentage, it is very easy. You can check it online also, and you have the standard ASTM standard also has it very clearly defined how much percentage of chromium is required. It is 18%. So you are higher in the chromium side. So you should hopefully be good with the fluid. You are more corrosion resistant. However, be very cautious of the rating. Could be that your rating might be inferior and you might, for example, from 300 flange rating, you might require it to be 600 flange rating or 900 flange rating, depending on that. However, fluid wise, you are good to go. Next component which comes in is going to be nickel. Now nickel, what it does is it adds stability at high temperature. Most applications, especially for instrumentation, you would see SS316. The reason is it has nickel, it has chromium, it has carbon. So it is comparatively hard, it has good corrosion resistance, and because of nickel, it has stability at high temperature. So for most applications, you will see SS316 being good, but that does not mean every single application. If your fluid is okay, if the piping material is carbon steel, if you don't need any high, especially high temperatures are not there, corrosion is not going to be there, then I prefer go with the carbon steel body. You will save a lot of cost. One more thing I want to add up here is, whenever you look for, this is for a bit experienced engineers, whenever you look for piping material specifications, you always see something called as corrosion allowance. If you select your valve material same as the pipe material, which is carbon steel, then what you need to be cautious also is that pipe material also has a bit allowance for corrosion, because pipes are going to be for kilometers also, so you can't always have superior metals. So what they do is they increase the thickness a bit that let the pipe corroded. So there's something called as corrosion rate per year. So the corrosion allowance is, for example, 6 mm or 10 mm. So that much area can get corroded and still the pipe is going to work well. If that is the case, and if the corrosion allowance limit is high, then remember, if your valve body is also of the same material, then I think it's a risky engineering decision. If the corrosion allowance is low, yes, you can go ahead with the same material, because our standards don't have, like the API standards don't have any specific clause, or at least I have not come across any clause which talks about corrosion allowance in our walls. So whatever is the thickness we assume. Another important thing is the trim material. According to me, do not be stingy on the trim material. Select the best, because the trim is going to experience highest amount of velocity, dp, everything. So the trim material should be at least same or higher than that of the piping valves. And on trims we will go in depth hopefully in coming sessions, but definitely that material selection is very critical. Third thing important for you is when it comes to high temperature is if you select dissimilar metals, if the trim is of a different material than that of your plug or your stem, each component has its coefficient of expansion due to heat. If they have dissimilar at very high temperatures, I'm talking about something like 600 degree, 800 degree, something of that level. There are certain applications which require such high temperatures. There you have to be very cautious of if you are selecting dissimilar metal. You can have extra stress which can cause the stem to break or some other issues can happen in the plant. Soft packing material. Okay, now packing material is something which is a little bit more trickier than this. I'll just give you thumb rules right now because we're running short of time. See, for packing material you need to see the fluid also. At the same time temperature becomes very important, and third is which Mayank mentioned, fugitive emissions. Overall speaking, packing wise, low temperatures 200 degree, 250 degree go for PTFE, goes higher temperature 400 degree, so go for graphite. If you have fugitive emissions, you usually start with first is V-type design, live loading design. If not possible, only then you start to go for bellows. It is the worst case scenario. If nothing works, your fugitive emission is extremely high, which is class A, then only you should think for a bellows seal valve. I'll just quickly wind up with just giving you at least the basic international standards. These are not all. If possible, I'll try to share maybe in Excel or maybe a list of all the standards, all the important ones. But here I'm just sharing is which are at least basic and crucial required. First is the valve C2C distances. Okay, here remember that ASME B 16.10 is one very important standard that your valve manufacturer should usually follow. The reason is piping will not wait for your valves to get manufactured, so they will have certain distance that they need to keep between two pipes. Why am I sharing this is in few of my experiences I have learned is, especially if you are giving offers or basically you are inviting newer vendors who have come into the field, they sometimes don't comply with this face-to-face dimensions, and at the site it will be a big hassle for you if you cannot match in between the two piping flanges. So first thing is, if you have a new vendor, if it's a reputed established vendor, they usually follow ASME B 16.10, or there's also an ISA standard which gives you the face-to-face dimensions. I can't go in depth right now, but when it gets to your RTJ and those designs, when the flange, there you have to be a little bit more, you need to calculate it exactly. If it's a new vendor, that is he complying with the face-to-face requirements or whatever is mentioned in your project. Second thing, if your valves are special, okay, I don't know if you have experienced this, but if there is some modification or it's a special kind of valve, then sometimes it will not comply with this face-to-face dimensions. So upfront you need to take the dimensions from the vendor and give it to your piping department, or else later you will suffer when the valve is manufactured. So this interface has to be very well known. Next, after that is going to be your flange standards. This is ASME B 16.34. If you look in the standard ASME B 16.34, it has various classes: standard class, special class. Usually 99.9% of your projects will be going with the standard class. Check the PT rating based on your standard classes. As somebody said, if your pipe material was carbon steel and your valve is 316L, so probably it might not have the same rating, so your rating will increase, and similarly the pipe rating has to be increased to match the valve with the pipe. Now this is something which a lot of people get confused with. You also have API valve standards, for example API 623 for globe valves or API 609 for butterfly valves. The point is, should I follow 16.34 or should you follow the API standard, is one query which comes in. Overall speaking, if you have API 623 for example, it is more stringent compared to 16.34 overall. So if that is the case, then if you have already specified API 623, then you are at a stringent requirement. So okay, fine, makes sense. If you have specified 16.34 but your client wants it to be an API valve, which is usually for the petroleum and the oil and gas industry, you need to specifically mention to the vendor that you need a valve which is manufactured as per the API standard as well. It will not be covered under ASME. For example, the stem thicknesses for a globe valve is higher. So that is how those things have to be definitely taken into care. Third is, which a lot of you mentioned, is the leakage class. Leakage class, I told you one important point. The leakage class mentioned is based on standard conditions. If your valve requires extremely high amount of tight shutoff, do not rely on control valve. Husky accident happened. Even the ExxonMobil accidents have happened a lot, where the control valve could not actually close. Because, and if you also read the API RP 553, which is also what we'll mention soon, in that also it is mentioned, especially for FCC units. This is a very common mistake that used to happen. Please avoid that. For fugitive emission standards, ISO 15848, TALFT. Here something for you to know is in ISO 15848 you have -1 and -2. So one of is where you do an actual testing of all the valves. Certain things where you have just type testing, so you basically test a particular valve and that is basically suitable for all the other valves. TALFT is basically very yet well known. It is usually used in German projects. When you specify ISO 15848, this standard itself is further divided in the sense, if you read the standard, it has 3 classes, A, B, C. A lot of the times engineers just mention the standard, and you should check in your specs, do they want a specific testing? Do you want it to be AH class or AB or BH class or C class? So H stands for whatever is the thing. If you're using helium, for example, whatever is the test gas that you use. So basically you have ABC. So if you don't mention, my understanding is vendors would consider C, which is the least stringent, which makes sense. If you have not mentioned, they will consider C. And if you wanted A and you say later, then it will be a big confusion, because this testing is not very cheap. It is a good process, and if all the valves have to be tested, if you go for that, then that is not easy. That being the case, be very cautious when you mention these standards. Second thing is the valve testing, and I wanted to cover calculations, but I was assuming we'll run short of time. So basically here I'll just mention is ISA 75, which has further divided into like cavitation and cavitation index, and all of those things will come here. And for control valve noise, 3 and 4, I think 3 stands for gas and 4 stands for liquid. So the noise calculations have to be done. This is just an overall overview which I'm giving, and then you have is your API RP 553. I definitely recommend you to read API RP 553. You will learn the recommendations for fluid, cracker, FCC units, etc. What you should do in those cases. So this is just an overview. I'll try to add up more standards also as we go, and then share with you the presentation. If I've made some mistakes while speaking, please forgive me. And thank you so much for your patience to listen.